Hello students, welcome. Previously Form 4, Topic 3, Lesson 5, we were dealing with factors affecting equilibrium. We have done number 1, which was concentration. So today, Lesson 6, we are going to proceed to second factor, that is pressure. So we are going to see the effect of pressure on the position of equilibrium. So we are saying a change in pressure will only affect equilibrium involving gases. It has no effect on those reactions in which both the reactants and products are either solids or liquids or even solutions or aqueous solutions, since they cannot be compressed or expanded. So we are saying if the pressure of a system in equilibrium is increased, the system will favor the direction that has fewer molecules or fewer moles or fewer volumes. So again, next we are saying if the pressure of a system in equilibrium is decreased, the system will favor the direction that has more molecules or more moles or even more volumes. So we are saying if the number of molecules of the reactants equals the number of molecules or moles of products, a change in pressure does not have any effect on the equilibrium position or on the position of equilibrium. Examples. Let's go to examples. We are going to start with example number 1. So we are told state and explain the effect of an increase in pressure on the equilibrium below. If you check here, we have hydrogen gas reacting with chlorine gas, giving us hydrogen chloride gas. So let's check now the number of molecules or moles or volumes on the reactant side. Here we have one molecule of hydrogen, another molecule of chlorine. So in total, the reactant side, we have 2 molecules. But when you check on the product side, again, we have 2 molecules of hydrogen chloride gas. That means the number of molecules on the reactant side equals the number of molecules on the product side. So it is this point. We are saying if the number of molecules of reactants equal to the number of molecules or moles of products, a change in pressure does not have any effect on the position of the equilibrium. That means this reaction, if we increase in pressure or we decrease the pressure, it has no effect. So we are going to say no effect on the position of equilibrium. No effect. And the reason we are saying this is because the molecules of gases in reactants and products are equal. Therefore, has increase in pressure has no effect on the position of the equilibrium. In question 2, we are told state and explain the effect of an increase in pressure on the equilibrium below. We have calcium carbonate solid, we are having calcium oxide solid and carbon peroxide as our product. So let's count the number of molecules on the reactant side. We have 0 number of molecules because here we have calcium carbonate, it's a solid, it's not a gas. So we have 0 molecules. So here we're having calcium oxide, this is solid, we don't want, we have carbon peroxide. Here we have 1 molecule of carbon peroxide. That means the product is having 1 molecule of carbon peroxide. Okay, here we are having increase in pressure. So what have we said if we increase the pressure? We are told here, if the pressure of a system in equilibrium is increased, we are told the system will favor the direction that has fewer molecules or moles or volume. That means this side is having few number of molecules or few moles. This side, calcium carbonate, because we have 0 molecules or 0 gas molecules. But on the product side, we have 1 gas molecules. So what are we saying? The equilibrium will shift to the left. That is the effect. So we're going to say the equilibrium shifts to the left. The equilibrium shifts to the left. Reason, this is because high pressure or increase, saying increase in pressure, increase in pressure favors the reaction with the less number of gas molecules. Less number of gas molecules. That is the reason. So we are saying the equilibrium shifts to the left. This is because increase in pressure favors the reaction with less number of gas molecules. Next, we are going to go to question 3. We are told the following reaction is in equilibrium in a closed container. We are having carbon solid plus steam, which is gas. We are going to get carbon 2 oxide gas and also hydrogen gas. So we are told state will given a reason how an increase in pressure will affect the amount of hydrogen. So we are going to check the amount of hydrogen, whether the amount of hydrogen decreases or increases. So we are going to check the side with the few number of molecules. That's where the equilibrium will shift, because we are told increase in pressure favors the side that produces less number of molecules. So here, carbon is solid, so we are not counting. We have steam, that's a gas. So we have here one molecule of gas, one gas molecule. So here we have carbon 2 oxide, 1 mole here, and hydrogen gas, another mole of 1 mole of hydrogen gas. So 1 plus 1 will give us 2 molecules of gas. And here we have 1 molecule of gas. So that means this side is the one that's having less number of gas molecules. So that means the equilibrium will shift to the left. That means the amount of hydrogen is going to decrease or to reduce. So we are going to say the amount of hydrogen would decrease, or we can say reduce. Reason, this is because increase in pressure favors, or we can say shifts, the reaction with few or fewer molecules. Hence backward reaction is favored. Full stop. That is our reason why the amount of hydrogen will decrease. So next we are going to go to Rome 3. That means factors affecting equilibrium. The third factor is temperature. So we want to see effect of temperature on the position of equilibrium. So we're saying effect of temperature depends on whether the reaction is endothermic or exothermic. So endothermic is the reaction that leads to the absorption of heat from the surrounding, and exothermic reaction is the reaction that releases heat energy to the surrounding. So we're saying an increase in temperature favors the endothermic reaction. That means the side that absorbs heat. Direction of the equilibrium, while a decrease in temperature favors the exothermic direction. That means the side that releases heat energy to the surrounding. Direction of the equilibrium. Examples. Number 1. We are told the following reaction is in equilibrium at 35 degrees Celsius in a closed container. So we're having 2 molecules or 2 moles of nitrogen peroxide gas, which is brown in color. Under equilibrium, we are going to get dinitrogen tetraoxide, which is gas, and it is pale yellow gas. So we are having the enthalpy change for this reaction, which is negative 92 kilojoules per mole, telling us that it is an exothermic reaction because of the negative enthalpy given. So we are told, state and explain the observation made when the mixture is heated at 60 degrees Celsius. So here we are having at 35 degrees Celsius. So that means when it is heated at 6 degrees Celsius, there was an increase in temperature. And if we check here, we are told an increase in temperature favors the endothermic direction. So if you check this reaction in forward direction, it is exothermic because we are going to get a negative enthalpy. But that means the other side, that in the backward direction, is the one that's having the endothermic process. That means we are going to have brown color of gas being intensified. So the observation will be brown color of gas intensify, or we can say pale yellow color of gas fades. Okay, reason? The reason will be, we are going to say this is because increase, and say increase in temperature favors the endothermic process or the endothermic direction. Hence the equilibrium shifts to the left, or we can say hence backward reaction is favored. Backward reaction is favored, or you can say hence the equilibrium shifts to the left. So number 2, we are told under certain conditions, carbon dioxide reacts with water to form methanol and oxygen as shown below. 2 moles of carbon dioxide gas reacting with 4 moles of water liquid, we are going to get 2 moles of methanol and also 3 moles of oxygen gas, and the enthalpy change for this reaction is positive for 1452 kilojoules per mole. So because of this positive, this forward reaction will be for an endothermic process. So what we are told, what will be the effect on the yield of methanol if the temperature of the reaction mixture is increased? Explain. So we are told, remember, increase in temperature favors the endothermic direction or the endothermic process of the equilibrium. So that means this is forward reaction is an endothermic process or endothermic reaction. Hence, the equilibrium will shift to the right. That means the yield of methanol will increase. So we are going to say the yield of methanol. The yield of methanol will increase. Or will be more. Reason? This is because the reaction is endothermic. Hence, increase in temperature favors endothermic process or forward reaction. Therefore, the equilibrium will shift. Therefore, or you can stop there. Therefore, the equilibrium position shifts to the right. Shifts to the right. That is the effect on the yield of methanol. Example 3, we are told sulfur peroxide reacts with oxygen to form sulfur 6 oxide as shown in the question below. We're having 2 moles of sulfur peroxide gas plus 1 mole of oxygen gas, giving us now 2 moles of sulfur 6 oxide gas. Sulfur 6 oxide gas, and the enthalpy change for this reaction will be negative 192 kilojoules per mole. So this is an exothermic reaction. That's the forward reaction. So that means backward reaction will be endothermic process. So I told explain the effect on the yield of sulfur 6 oxide by lowering the temperature for this reaction. Lowering means decreasing the temperature for this reaction. So that means if we are having an exothermic reaction and we decrease the temperature, that means the equilibrium will favor the exothermic process. So that means forward reaction will be favored and the yield of sulfur 6 oxide will be more, or the yield will increase. So we are going to say the yield of sulfur 6 oxide will be more. We can say increases. Reason? Because this is because lowering the temperature for exothermic reaction shifts the equilibrium position to the right. Shifts the equilibrium position to the right. Hence, forward reaction is favored. Full stop. That's our reason. Part B, we are told raising the temperature for the reaction. Raising the temperature means increasing the temperature for the reaction. And here we are having exothermic reaction. So that means if we increase the temperature, that means it favors the endothermic process, and that's backward reaction. That means the yield of sulfur 6 oxide will decrease or reduce. So we are going to say part B, the yield of sulfur 6 oxide decreases, or what you can say reduces. Reason? This is because decreasing or raising the temperature, raising the temperature for an exothermic reaction shifts the position of equilibrium to the left. Hence, backward reaction is favored. Backward reaction is favored. So we are done like that. We go to Romeo 4. That means the other factor that affects equilibrium, which is catalyst. So effect of catalyst on the position of equilibrium. We are told a catalyst has no effect on the position of equilibrium. It only alters or speeds the rate at which the equilibrium is established or is attained. Example, a dynamic equilibrium is established when hydrogen and carbon dioxide reacts as shown below. So we're having hydrogen gas plus carbon dioxide gas. We are going to get steam plus carbon dioxide gas. So we are told what is the effect of adding bonded iron catalyst on the position of equilibrium. We are told to give a reason. So remember, we are told a catalyst has no effect on the position of equilibrium. So we are going to say it has no effect. It has no effect. Reason? This is because a catalyst has no effect on the position of equilibrium. Remember, it only alters the rate at which the equilibrium is established or attained. So next we are going to go to some industrial application of chemical equilibriums. The application of chemical equilibrium helps a manufacturer in determining the optimum conditions required in setting up a plant. So here we want to do two processes. The first one is the Haber process, which is the large-scale manufacture of ammonia and the contact process, which is the large-scale manufacture of sulfuric 6 acid, which is the contact process. So the first step, we are going to see reactions in the catalytic chamber. Here we are having nitrogen gas reacting with hydrogen gas, 3 moles of hydrogen gas, giving us 2 moles of ammonia gas. And the enthalpy change for this reaction is negative 92 kilojoules per mole. So when we are dealing with the reaction in the catalytic chamber of the contact process, we are having 2 moles of sulfur peroxide gas reacting with 1 mole of oxygen gas, giving us 2 moles of sulfur 6 oxide gas. The enthalpy change there will be negative 197 kilojoules per mole. So next we are going to see the optimum conditions. When we are dealing with optimum conditions for HAPA process, we have to talk about temperature of 450 degrees Celsius. In the contact process, the same, temperature of 450 degrees Celsius. When we're talking about pressure in the HAPA process, we're having pressure of 200 atmospheres. But in the contact process, pressure of 2 to 3 atmospheres will be used. So in the side of HAPA process, we are going to use finely divided iron catalyst. But when you're dealing with that side of the contact process, vanadium 5 oxide catalyst is used, which is written V2O5, vanadium 5 oxide catalyst. Then we're saying iron is preferably used instead of platinum catalyst in the HAPA process. Reason being because it is cheap, that's one, and it's less poisoned compared to platinum catalyst. So during the exam, you can be told, state 2 advantages of using iron or finely divided iron instead of platinum or than platinum. So here, vanadium 5 oxide is preferably used instead of platinum catalyst because it is cheap. Thus, vanadium 5 oxide is cheap and it is less poisoned compared to platinum catalyst. That is it in both the HAPA process and also that side of the contact process. So we are told for maximum or high yield of ammonia in HAPA process and sulfuric 6 acid in contact process, there must be a low temperature and also high pressure. But if you remember, low temperature, we are told the disadvantage of using low temperature is that it makes the reaction is low. Then the disadvantage of using high pressure is it's expensive to maintain because high pressure requires expensive apparatus, which requires high expenses. Hence, makes the process or the plant to be expensive to maintain. Next, we are going to go to the extended question. We are having question number 1. Kindly check. Next, we are having question number 2 as our extended question, as you can see. Then next, we are having that's question number 3, as you can see. Then lastly, we are having question 4. That's question number 4. And that ends or makes the end of chapter 3 from 4. In our next class, we are going to introduce to the 4th chapter, that's electrochemistry.